Yeah. Essentially, I will speak about what are the multi-band superconductors are, what is the motivation of this talk, studying the Innsbruck-Landau theory, which is the most simplest theory of the theory of superconductivity. And the purpose of it, of course, to extend the theory to use it in the correct way in the multi-band environment. So I will introduce it a little bit different way, using the expansion of the small parameter close to the TC. And then I will go to the what is called the extended Innsbruck-Landau theory in the correct way. And the immediate application of this theory is the study of the Bogomolny point, which is the special form of the theory of the superconductivity, where the transition happens between the type 2, or crossover happens between the type 2 and the type 1 superconductors. And I will show what happens between this, or close to this point, in the multi-band environment. So essentially, I have nothing else to say after this beautiful introductory lecture of the previous speaker. What is the multi-band superconductivity? Essentially, you can think of this as the superposition of the condensate being in the same material, but of course it's a much simplified picture, and it's only good for the initial intuitive consideration. But the topic expanded in recent years and due to the discovery of multi-band materials, where you can clearly see the multi-band picture and you can measure this. Of course, theoretically, it has been for many years, people extended the superconductivity theory to the multi-band system, but only during the last decades it became experimentally so clearly demonstrated. But also there are some other systems where you can also see some signatures of the multi-band superconductivity, and obviously these are where in particular you have the multi-band appearing due to the geometrical quantization, the quantum size effects of the Blatt-Thompson, and now with the superconductors of being the small size, and in particular, for example, in the Fermi gas, also called Fermi gas systems, where you have the quantization due to the trap of the geometrical sizes of the trap. And the particular inspiration of this talk is the experiments where you can see the stable configuration of the vortices, which is not being showing the signs of either the type 1 or the type 2 superconductivity. And these are the particular, you can see here the comparison between the clear type 1 superconductor. Here is the clear type 2 superconductor, and what the configuration of vortices, what you can see in the magnesium diboride. The subsequent experiments showed even more exotic structures, like, for example, chains appearing. It's quite stable chains. And recently, the current group, they produced the structures which really looks like worms of some kind, the labyrinths and so on. And there are multiple, apparently multiple kind of transitions between these structures if you decrease or increase the magnetic field. So, of course, the simplest way to study the system is to use the Innsbruck-Landau theory, because in macroscopical theory, in the homogeneous environment, it's simply so numerically costly to calculate. And this is the easiest example of this kind, used many times and derived directly from the microscopical theory. You use the Innsbruck-Landau-like functional extended here to the two-band system. So the only here is all the things are calculated for a single band, and the coupling between the bands exactly assumes the assumption that you have the pairing happening only within a single band. So the interaction looks like the Josephson-like coupling. Of course, if you vary this functional, then you produce nothing but two coupled Ginzburg-Landau equation, and this is a standard basis for so many works in studying the vortex configurations in such systems. This simple model has many problems, and unfortunately it is not so well if you consider this problem in terms of the Landau theory of the phase transition, because Landau theory of the phase transition predicts that you actually have to have the number of bands dictated by the symmetry of the system and not by the number of bands. So you must have the particular dimensionality of the irreducible representation. And actually there is a problem which is closely related to this. This is called the accuracy inconsistency of the multi-band generalization of the Ginzburg-Landau theory. This has been noted long ago by Galikman, Zaitsev, and Kresin in studying the multi-band generalization of the Ginzburg-Landau theory, and recently kind of rediscovered by Kogan and Shmalyan, and independently by Shanenko. And the problem is that if you consider the Landau theory as a theory of small parameter, which is the only small parameter in the system which has proximity to the critical temperature, then you can compare the accuracy of all the contributions. And the accuracy of all the contributions close to the TC is given by the order parameter itself, which is the square root of this small parameter, and of the coherence length, which is the inversely proportional to the square root of this parameter. And then the change, the spatial changes of the order parameter is, of course, scales accordingly. So if you count all the contributing terms, then you will see that in the Ginzburg-Landau theory, then you have the all terms, all three terms in the Ginzburg-Landau theory, they have exactly the same scaling with this parameter. This is, of course, for zero field. Then the conclusion is that a single component Ginzburg-Landau theory, it accounts for all terms exactly of the same order and only for these terms. In the generalization of the two bands, for example, this simple conclusion breaks. And you can immediately compare, if you write this two Ginzburg-Landau equations and try to find its solutions. And then you will immediately see that solution is produced by the infinite series of this tau, and therefore it simply breaks the standard law. This accuracy of the solution now exceeds the accuracy of equation, and this is what is called the accuracy mismatch. So in order to reconcile the accuracy of the derivation of the theory and the accuracy of the solution, you have to apply the reconstruction procedure, and this has been done in the work which I have mentioned before. And if you do so, then you will see immediately that the order parameters, well, here I call this the order parameters, but these are actually something. These are all proportional to each other, and you can introduce the function which is really the old parameter in the system, and there is only one. The two-gap system, two-band system, is defined by the Ginzburg-Landau theory, which has only single order parameter, which is exactly in agreement with the Landau theory of the phase transitions. So if you really want to describe the many-body superconductivity with the Ginzburg-Landau theory, you have to go beyond this, and you have to essentially do the same matching of accuracy of your theory. So you have to expand the functional beyond the Ginzburg-Landau, and you have to take into account higher powers of this expansion over tau and match exactly the accuracy of the both expansions. This is what you have to do. And the first part of this problem has been done long ago. Actually, it started from the Newton and Stewart, and this functional which I have written here has been obtained many times. It's not a simple problem, so there were many mistakes in writing this. But these are the final form of this functional, which appears very simple. And of course, the black terms are this Ginzburg-Landau theory itself, and the blue terms is the extension. If you write the extremum of this functional, it seems that like you will have the extension of the Ginzburg-Landau theory in terms of the equations, but you can immediately realize that these equations are nearly useless. Because this, first of all, this problem is unclear which terms you have to keep. This will be, this is usually done on the basis of the intuition. But the real problem is that with this functional you will have unphysical problems, because first of all, this functional is not restricted from below, and this is a problem. And the second, perhaps, is what most important, is this term which appears as the fourth order derivative in the system, and it will lead to this, to that the changes, the spatial changes of the system, the spatial changes of your order parameter will be less than the Ginzburg-Landau correlation names, and much less. Actually, it tends to shorten the oscillations of the order parameter. So this is really unphysical, and therefore this functional can be used if you know approximately what your solution is, so you will substitute some sort of ansatz. You can actually solve this problem, and this has been initiated in the work of Lukyanchuk and almost more than 10 years ago, but the formal expansion has been produced only recently by Shanenko and by myself. So essentially the idea is you have to use the expansion of all quantities in the functional using the same small parameter in the system, this tau, and this will produce the formal perturbation theory. So this is the how it would look like. I only kept the terms which are important for the next to the leading order correction to the Ginzburg-Landau theory. And you can calculate, of course, this for any model, many microscopical model you use. This is a standard, more or less. So here is the result for the clean limit, this standard constant to calculate. So if you then match the accuracy, the equations which you will obtain after, as a result of the theory, the first, the lowest order, then you will obtain simply the equation for the critical temperature, which is good. Then you obtain the Ginzburg-Landau equation itself of the order of tau 3/2. And then you will obtain the correction this in the form of the linear equation. So here is the linear equation for this correction, and here is the inhomogeneous term, appears on the right side. And this inhomogeneous term looks very ugly, but actually very simple, if you take into account that this is a solution of the Ginzburg-Landau theory itself, and it only depends on the Ginzburg-Landau theory solution. So, in principle, you can obtain the higher orders as well, and they will be all given by the linear equations. And by doing so, you will have to you will get rid of the only physical solutions in the system. So then we come to the main point, where how to extend this for the multi-band system. Actually, the sequence of the derivation steps is exactly the same. So you have to do the multi-component microscopical model. You will derive the functional for the order parameters, and that will be beyond the Ginzburg-Landau model. Then you will obtain apply the perturbation expansion with respect to tau, and of course you have to collect all the terms in this expansion. So here I will give only the first equation of this kind. This is the comparison, what we will obtain to the single component system and for the two component, for the two-band system. And this is equation that already appears in the previous talk. This is the equation for the TC. It now contains two components, so then it's the solubility of this equation is that the zero order of this determinant, which defines exactly the TC, of which you have two TCs, and you have to take only the largest. But you immediately see here that the condition of the solubility of this equation is that you will have the solution of this equation appearing in the form of the eigenvector of this matrix. And therefore, there is only one parameter function which defines the solution on this level, which you can call the single Ginzburg-Landau parameter in the system. And this is precisely what was the outcome of the work of the Kogan and Schmalian. If you go to the two bands, then what you will see is that essentially you will obtain the same kind of equation as in the single component. Here it will also contain the admixture of the first correction. But if you project this equation, which is called the reconstructing procedure, then you will obtain the equation for this order parameter, single order parameter in the Ginzburg-Landau system. Then you will do this extension, and you will obtain the correction to the Ginzburg-Landau theory. And essentially, this is, well, I forgot to mention, of course, that all of this is correct unless you have the additional symmetry in the system, in which, in this case, you will have more than one order parameter already on the Ginzburg-Landau level. So, for two bonds, the corrections will be exactly the same, appear in exactly the same level, in exactly the same step. So then you will obtain the linear equation, which will govern now by two components of the systems, unlike the level of the Ginzburg-Landau equation, where you have only one component of the system. So two components in the system will appear, but only on the level, on the correction of the Ginzburg-Landau equation. And in the symmetry language, these are actually the terms which defines the admixtures of the other irreducible representation of the symmetry group. So phenomenologically, this has been done already in the 19th. Now you can only formally recover this, formally derive this from the microscopical equations. And now with this, what I have described, I will come to the point where I apply this theory to study the Bogomolny point. And the Bogomolny critical point is the superconductivity. It's not often used, this term, but this is essentially where the superconductivity changes from the type 1 to the type 2. And we know that in the Ginzburg-Landau theory, it is defined by the critical value of the Ginzburg-Landau parameter, the ratio between the two lengths. And when this is equal to precisely 1 divided by the square root of 2, then you will have the crossover between the two types of the superconductivity. The special about this point is actually that it is infinitely degenerate. So if you calculate the energy of the system, then you will see that the Gibbs energy is precisely 0 for all configurations in the system. And in particular, it means that the vortices do not interact in this, and this has been shown in a little bit different context than superconductivity by Bogomolny and Einstein in 1973. The mathematical reason is well known. This is the so-called Sarma condition that simplifies the equations immediately, and you have this self-duality condition relating the absolute value of the order parameter with the magnetic field. But this is a very special point where the superconductivity is not actually defined, and of course you do not have either type 1 or 2 type 2 superconductivity in the completely degenerate system. But what is important is that it is only so a single point, temperature independent, in the Ginzburg-Landau theory itself. And in macroscopical theory, this degeneracy is, of course, should be lifted at any temperature which is less than the critical temperature. And the critical kind of behavior, the strange behavior, will appear in the finite interval which you have to calculate. How this happens is it's quite amazing because you may have the infinite degeneracy precisely at this point for any topological configuration, for any multi-vortex configuration, for any lattices, for anything. And for each of those configurations, you can define the line of the zero energy, and this is where this configuration can no longer exist. And therefore you have many, infinitely many such lines, and not only the configurations, but properties of these configurations, because for example, vortices becomes attractive at long ranges and repulsive, still repulsive at the short ranges. And so in between these states, between the type 1 and type 2, there are maybe multiple of states and maybe multiple of transitions. And this actually has been noted long ago, that something strange happens here, and this has been called the type 2-1 superconductivity. Although it has been assigned only to the long-range attraction between the vortices. So now we can apply this formalism, extended one Ginzburg-Landau beyond the extended Ginzburg-Landau formalism. And the idea is very simple. So essentially you have to construct a perturbation theory not only with respect to the small parameter proximity to the temperature, but also with respect to small deviation from the Bogomolny point. And if you calculate this, this will appear quite a complicated expression. But you have to remember that this is a solution of this Ginzburg-Landau theory at the Bogomolny point. So it enormously simplifies, and actually it takes into account both bands in the system and both differences between the other parameters in the system. So in calculation, all the contributions of the bands are reduced to a single function, which is a solution of the Ginzburg-Landau equation. So then you can really simplify this expression, and this appears as a number of constants. So the only solution part, the solution-dependent part of this expression is given by these two integrals. And this is the advantage of doing the calculation using this formalism. The multiband contributions here are marked in red, and they are absent in the single band case, although all the parameters say that all the parameters are actually affected by the presence of multiple band structure, but these contributions are simply not present. And then you use this calculation for the Gibbs energy to compare the energy of all configurations of whatever you like. And essentially, this you can apply to the single band system and to the particular point which is close to the transition to the crossover between the type 2 and type 1 superconductors. And you know that this has been done actually experimentally. The type 2 magnetization is characterized. It's first it goes to the Meissner phase, and then the mixed phase it steadily goes to 0. For the type 1 superconductor, it goes and drops. And there is a mixture between the two, and the magnetization curves. It just rises, then drops, and then goes steadily to 0. Well, this is defined as type 2-1 superconductors. And if you compare what is available, the data available experimentally, and compare with the calculation which appears from the extension of the Ginzburg-Landau theory, for the simple band system, it's a universe parameter for the clean system. You can calculate this. This doesn't depend, well, it does depend on the model, but the model is standard here, the spherical Fermi sphere. So then you will see that amazingly it matches exactly very close to the experiment. As an example, I calculated here one thing which is usually missed in the standard analysis of the vortices. These are the vortices with the multi-quantum flux. And you can see that what happens is that if you cross this parameter, this delta K0 is precisely the Bogomolny point, then the vortices which on the type 2, the vortices with the single quantum are the most favorable, and the vortices with the higher quantum are less favorable, reverses the order. So gradually, vortices with the higher and higher flux becomes more and more favorable. And if you calculate the critical parameter which corresponds to this multi-vortex structure, then you will see that it goes down and approaches the it goes to the solution of the domain wall. So in the diagram, it would look like this if you consider only single vortex cases. So you will have this attraction of vortices, and here type 2 and type C, they become 5 minutes?
3 minutes.
3 minutes. Okay. So this is the diagram where you have the multi-quantum vortices. And what I'm going to do now is simple. I will show the picture. If you apply this to the critical interval in the multiband system, what happens is that this critical interval enormously expands, orders of magnitude. And this is systematic expansion. You can find nearly for all parameters in nearly for all type of parameters in the system. The origin of this is physical. This is the introduction of the non-locality effects, which are enormously increased in the multiband system. And essentially, this is one of the reasons which I would prefer to call this the critical type of the superconductors. So here is my conclusion. I have presented you the expansion of the extended version of the Ginzburg-Landau theory and demonstrated the considerable enlargement of the critical domain around the Bogomolny. Thank you for your attention.
Yes, Igor.
Yes, I'd like to ask one question. I'm still struggling to understand how it can be connected with Landau theory of the phase transitions, because in your construction, the leading order in tau, you get a system of U and Kogan-Schmallen and Kogan-Schmallen, just get a system of equations which are exactly the same as V1 cross V1. Equation with standard equation for V1 cross V1. There is no phase locking term of the leading order, and then phase locking term appears only in the next to leading order, so that it would mean that if you hit system, you get hit the system with the symmetry explicitly broken to V1, you became V1 cross V1 is the critical point. So I don't see how such a construction can have a solution. So could you, how could this system obtain have solutions to what's your take on this? How is it consistent with Landau theory?
Well, the Landau theory, if you have no special symmetry between the bands, then essentially, well, Landau theory predicts that you will have the dimensionality of your effective functional be given by the dimensionality of the reducible representation of the symmetry group. And
my question is simple. Sorry for interrupting you. So if you have a system of equation in the you and Kogan-Schmallen have a system of equation in the quadrant which is coupled only by vector potential. So this is exactly the same system as Ginzburg-Landau equation V1 cross V1.
without the coupling, only without the coupling.
Okay, but we are already running behind. Is there any other short question? Yes.
Ask you a practical question. How deep can you go into the superfluid phase far from the critical temperature?
Here I have to show you one picture. This is for the single band. This is the Ginzburg-Landau BCS extended. Then this is for multi-band, for two-band system. This is the one variant of the Ginzburg-Landau, the other one with the coefficients, and this is extended Ginzburg-Landau for one band for the larger and for the smaller and for the critical field. And this is the calculation of the vortex attraction with the microscopical theory, and this is with this extended Ginzburg-Landau. So you can see the comparison is quite up to 0.4.
Okay, so let's thank the speaker.